All right, let's get started with section 2.2, matrix multiplication. Before we get to matrix multiplication, we're going to go over matrix scaling and addition between matrices. And this works the same as with vectors, which are really just single column matrices. So just to give a quick example, uh, I2, remember, means the 2 by 2 identity matrix, which looks like so. And the 0 matrix is just the matrix where all the entries equal the number 0. So whatever size of thing you're talking about, like here, the other matrix is 2 by 2, so we can just assume that 0 is 2 by 2 as well. And anyways, what it means to multiply this matrix by the scalar 3 is probably what you would guess. You just multiply all the entries by 3. So 3 times 1 is 3, 3 times 0 is 0, 3 times 0 is 0, 3 times 1 is 3, so all the entries like that. And then to add them, we're just going to add all of the corresponding entries. And adding the zeros, of course, doesn't change those entries. So yeah, you still get the same thing as 3 times I2. Okay, with B, well, we can do this multiplication by 2, but at this point, these are differently sized matrices, so there isn't really a good way to define how to combine these. I believe with MATLAB, it will let you do it. It will just sort of like add in zeros in the places that it needs to make it so these can be defined, I think. But in this class, anyways, we're going to just say this is undefined. And in part C, this just gives us a nice way to define a matrix in terms of other stuff, like using augmented matrix notation. So we're just saying we're adding on another column of it, and then this part is the 3i2. And then subtracting just means subtracting each of the entries. So that gives you 10 minus 3, 11 minus 0, 12 minus 0, 13 minus 0, 14 minus 3, and 15 minus 0, which gives you this result. Okay, so that's pretty straightforward. We're not going to spend much time on that, but we do want to notice that we have basic properties of matrix multiplication. We got a commutative property, and this works just like it does with vectors, so maybe this is no surprise. We got an associative property. We can move the parentheses around like so. If you add the 0 matrix to anything, it doesn't change it, kind of like what we just saw with example 1a. We got a couple distributive rules. We can distribute scalar multiplication over scalar addition. We can also distribute scalar multiplication over vector addition like this. It works both ways. We got an associative rule. And there was a theorem in section 1.3 that basically said all these things with vectors. And the proofs work the same way. They're true because there's a corresponding property of real number addition and multiplication that applies to each of the entries. So yeah, you can prove a couple of those for homework. Now, matrix multiplication is where it gets complicated. The goal is to define the matrix AB so that the product AB times X is the same as the product A times BX. So to give us this associative sort of property. just like we saw happen in exercise 2. And to see how this should work, let's suppose we have a matrix A that has C columns, A1 through AC, and R rows. So each of the entries is an R vector. And B is a C by D matrix. So now it has D columns, but each of them is in RC. Each of these columns has C entries in it. So let's check our understanding of just how like Bx and A times Bx should work. So the matrix B defines a linear transformation, and by that I mean like T of x equals Bx, basically, that takes any input vector x, but how many entries should x have so that B times x is well defined? Well, the number of entries of x must equal the number of columns of B. Because what B times x means is taking a linear combination of the columns of B using the entries in x as weights. So x is in our D for that reason. And that gives you an output vector. Well, this linear combination of the columns of B are columns in a matrix with C rows. So every one of these vectors must be in RC. So a linear combination of them is in RC. We can write this as x1, b1 plus x2, b2 plus yada 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 plus x, d, b, d. Now, we're saying that A times B times x is well defined here, right? So in order to do that, the number of entries in Bx has to equal the number of columns of A. So, scooching over here, A times the quantity Bx is defined. I'll just substitute this notation for Bx over here. And we had a theorem that says the matrix vector product is a linear transformation. In other words, that there's a distributive rule here. So we can write this as A times each of these columns, like so. And the other part of that linearity theorem was that there's like an associative rule where you can take a scalar out and multiply it first, like so. Or I should say, you can multiply the A times B1 first and then scale by x. Like so. And at this point, what we have here is a linear combination of some vectors using the entries in x as weights. The definition of a matrix vector product is you can write this as the matrix where the columns are the vectors you're doing a linear combination of, like so. And the vector you're multiplying by has those entries as weights. So this is what AB should be to make it so A times B, the product multiplied by x, is the same as A times the product Bx. Because we started with A times the product Bx, and we can see it's the same as this matrix times x. Neat. Okay. So yeah, here's that definition that we're describing here. If A is an R by C matrix and B has these columns, each with C entries in them, then the product is the R by D matrix, where each of the columns is A times one of the columns of B. And remember, each one of these is a linear combination of the columns of A using entries in that column of B as weights. Now, let's notice something about the size of this. Like we started with R by C and C by D, and the C's are the same. Those have to match up. And the result is R by D, like so. It's sort of like the C in the middle cancels out in a way. Okay, let's look at example 2. Now, maybe the first time we do this, I'll show like a lot of work, but after you've done this a few times, you don't need to show the work. Once you get how it works, you can skip some steps, but I really want to be a little explicit the first time around. So here's A, and here are the 3 columns of B. So we're going to do A times the first column, negative 1, 0. A times the second column, 4, 3. And A times the third column, negative 2, 1. And let's work each of these out. Remember, each time we're going to be taking a linear combination of the columns of A using the corresponding entries in the vectors from B as weights. So for example, the first one, we're going to do negative 1 here times the first column of A, which I'll write like so, plus this 0 times the second column of A. And that's what we get, like so. So you can see how the negative 1 and the 0 are scaling the columns of A there. Then let's do the same thing with A and 4, 3. We're doing 4 times the first column of A plus 3 scaling the second column of A, like so. And then for the third column here, we're going to do negative 2 times the first column of A, like so, plus 1 times the second column of A. And each of these, remember, is one vector. So we have a total of 3 vectors. And I mean, you could write the extra parentheses around everything if you really want, but I don't know if that helps. So what you get is the following. Okay, let's look at B times A. Well, what we would be doing is B times the first column of A and B times the second column of A. And I said what you would be doing because you cannot do this. Each of these is undefined. Because the number of columns of B is 3, and that doesn't match up with the number of entries in these vectors we're trying to multiply it by. So yeah, notice how we said in the definition here that the C and C need to be the same thing. The number of columns of the matrix on the left need to be equal to the number of rows of the matrix on the right. So yeah, this is a weird thing about matrix multiplication. A times B is a 2 by 3 matrix. And if we think of the combining the sizes, it's because we have A is 2 by 2, and we're multiplying that by 2 by 3, and we saw how like the middle number sort of cancels out, and you get a 2 by 3 matrix out. Here with BA, we're doing 2 by 3 because that's the size of B, and trying to multiply that by a 2 by 2 matrix, and we have this mismatch here with a 3 and 2. All right, sounds like a good time to take a break. Let's do example 3 in the next video. I'll see you then.